Hello, my name is Brendan Alvey, and I'm a PhD student at the University of Missouri, and I work under Dr. Anderson in the Mindful Lab. So today I'm going to be presenting this paper that we worked on with some folks at the U.S. Army. It's called Characterization of Deep Learning-Based Aerial Explosive Hazard Detection Using Simulated Data. All right, so the sort of starting idea here is that we can now generate photorealistic imagery using free tools like Unreal Engine 4 and 5 and Unity, Blender, things like that. And we can use these tools to now give us really accurate ground truth that we can use to train machine learning algorithms. We can also use these tools to generate a greater data set variety than we've kind of ever seen before. So, really in the real world, a lot of times when we collect data, it takes a lot of time and money to not only collect it, but then to also label it. And with simulation, we can really do all this stuff automatically and save ourselves a lot of time. So deep learning has always been really good at solving these really specific data-driven problems, but it's been bad at telling us like how it solves those problems. Uh, but I would pose the question of, do we really need to know exactly how the machine is doing it, right? So the way I would think about it is like if you think about humans, right? Each human has about 100 billion neurons, and each of those is connected to about 10,000 other neurons on average. But we can still accomplish a lot by just understanding how humans behave in a variety of situations without really needing to know like the specifics of what's going on in our brain. And really, I would say, like, can we do this for machine learning and AI models? Can we treat them as a black box and just evaluate their behavior under a variety of conditions? And really, that's going to be the goal of today's talk. So, kind of two big things. We're going to be using simulation to remove the data bottleneck using Unreal Engine and AirSim, and then the big idea here is I'm going to try to do some form of basically like explainable AI through simulation. I'm going to try to characterize one of our pre-existing models for explosive hazard detection by basically systematically sampling the operational space. But the idea is here you could do this for your sort of problem set and do a sort of similar thing. So the big picture is that you start with training a model, and you can train this, however you want, neural nets, evolutionary computation, fuzzy sets, whatever. And then you're usually going to deploy this model out there in the real world or in some simulated environment. You're going to evaluate the model's performance, right? Either in real simulation or a combination thereof. And then you're going to identify the model deficiencies. And that's, part of what this paper is about, is characterizing the model, getting an idea of how well it's doing under a variety of situations. And then you can have an expert come in the loop and really help you select these scenarios for collection, which then you can use to generate, use to collect more data, either simulated or real, which then you can feed back into your model, and then kind of continue this loop until you've trained your model that does the best. And really the gray stuff here is stuff that we haven't quite done yet. We want to close this loop, but we've just really tackled the blue parts yet, and that's what we're going to talk about in this paper, or in this talk. So we did an explosive hazard data collection using AirSim and Unreal Engine. If you're not familiar, Unreal Engine has like tons of 3D content that's available now. We've got either through their marketplace or through TurboSquid or PhotoScan and Quixel. You can get really awesome content and set up your scenes really quickly for relatively cheap. You can use this content to create automatically labeled data, like I've been saying. So this is what we did. We started and we put explosive hazards under a few different, sort of on this just gravel background, a few different types of explosive hazards. We can generate basically the color images. What we do is we convert it to grayscale because we don't really want to queue on color necessarily. Say if a landmine was painted a different color, we don't really want to miss it. We just want to look for like contrast and shape sort of features. So we've converted to grayscale. But one of the really great things is that AirSim gives us per pixel labels, right? So we can get these per pixel or perfect image segmented image here, which we can then overlay with or put our axis line bounding boxes on top and train basically our yellow V5 or 4 in the sort of the usual way. And if you're interested in doing sort of something like this or setting this up, something like a automatic collection for yourself, take a look at our related work. We've got some tutorials and a Git repo here from a paper that we presented at WAMI just a couple weeks ago. So this is one use case that we did. We took for each basically like fixed sun angle and standoff radius, we iterated through a bunch of different camera angles in a hemisphere around the target. So each one of these basically like vertices was a look at the target. We used simulation instead of real data because there's really a short battery life on the UAVs, and in simulation we don't have to worry about that. Also, there's sort of no fixed sun angle, right? The Earth is always spinning, so if we wanted to have shadows at a certain, length or position, then we really only have that for an instant in time, and after that, it's gonna, the sun's gonna move just a little bit and stuff and change things. So also, ground truth is hard to get, especially not just like having targets labeled, but if you want dense depth or surface normals or perfect odometry, all these things are really hard to get in the real world. But in simulation, it's just at our fingertips. And really, I just challenge you guys to think about, for us, there were some things that were difficult or slow to do in the real world that simulation has really removed this bottleneck, and now we can test all our other ideas. So, I challenge you guys to think about like what are your variables that you guys would want to simulate, or what things can simulation help you guys with. So for our experimental results, the first thing we did is we trained a model on a limited explosive hazard data set. We had 4 different target types and 3 different runs. Uh, we also tried training a model that was only on simulated data, simulated explosive hazard data, and we can already see a pretty big improvement over the real data alone, this limited real data set alone. And then what we did is we took targets, we put them on basically a benign background, and we extracted basically target templates, so we can have the targets themselves and their shadows all sort of encoded here in the alpha mask, and so we can use that to insert them into real images. So we have basically a real background here, and we've placed targets in here. So none of these targets are actually real; they're all just simulated and placed in here, and that did really well. And of course, the combination of all 3 did the best. And you can read the paper if you want some more details. So I'm going to go pretty quickly over this plot. This is just going to be how I'm going to visualize our result in the next 2 slides. So on the left-hand side, what we did is this is a sample, just a toy problem. Imagine a detector that's really good at detecting nadir, so it gets almost perfect detection at nadir, but really poor detection at low sort of elevation angles, and really is uniformly good across all the azimuth angles. And then on the right hand side here is if we vary the sun angle. So you imagine each of these sort of big little circular plots is one of these on the left that's kind of been shrunk down. So this sort of nadir view is the center, but as you move the sun angle or sun elevation angle, you move outwards, and as you move the sun azimuth angle, you move around the circle here. So what we did is we did an altitude comparison. I'll just go really quickly over this. We went from 20 to 100 meters. You can see at 100 meters is basically almost a contrast detector. But the takeaway here is if we look at the all plot, the larger the dots, the higher the variance, and the color is based on the average confidence. So what we see is that we really get better detections near the front of the target, and lower, and more reliable detections near the front of the target. The back of the target seems to be particularly difficult, especially when we get too close to it. Similar thing with the environment comparison. We did 3 different environments. We had benign, gravel, and grass, and really you can see pretty much a similar story. It's tougher to detect this particular target from the behind, from the back of it. Usually that's always in shadow. You can kind of see how it's placed. The target's kind of at a slant. So this all kind of makes sense. But it's nice to see it all systematically laid out and really just visualized. So I'm going to wrap it up here. We think that simulation is really ready for everyday AI ML use, right? Tools like Unreal Engine 4 and AirSim are making getting abundant, automatically labeled data just accessible. Big players like Google and Tesla are already doing this. The photorealism gap is closing, so I mean this stuff is only getting higher and higher fidelity, and it's getting easier and easier to work with. The ground truth is really awesome to have. And really just to conclude is simulation can help us better understand these existing systems and train better models. So for us, we were able to evaluate an existing model, and we were also able to train a model that did better than not having simulation in there. And really, so for the future work here, we want to close that loop. We want to have select the data and feed it back in. We want to be able to detect or be able to determine optimal detection parameters like the ideal camera angle and standoff distance. We also want to be able to have some linguistic summaries of everything here, so we can say like most native views have high confidence. And finally, we want to explore more of this XAI and SIM collection. And that's all I have today. So thank you for listening, and I hope you enjoyed the talk.